Mankind has always been governed by the pace of time with its dependable regularity. The rotation of the Earth gives rise to day and night, and its orbit around the Sun gives us the seasons of the year. All living things on Earth depend upon it. Many of man's most ingenious inventions have attempted to measure the passage of time, from the first rudimentary clocks to the exquisite detail of a gentleman's pocket watch. We have used our knowledge of physics and engineering. The study of the pendulum led to the first clocks that could both subdivide the days and count them accurately. But our story really begins with one of the greatest engineers that Britain has ever produced, John Harrison. In 1714, he set out to design a clock that would vastly improve navigation at sea and avoid some of the terrible shipwrecks that were occurring. To calculate a position, a navigator needs to know the time aboard ship and the time at his home port in the same moment. Harrison intended to make this possible.
Hello everybody. My name is Heidi Burgoyne, and in the next hour or so we'd like to tell you a little bit more about man's attempts to measure time. Here on the bench in front of me we have a model version of the pendulum part of one of John Harrison's clocks, and we want to compare this to the simple pendulum clock that you might well be familiar with. Now, the pendulum clock that was invented in the 17th century by Galileo and Huygens was a revolution in practical timekeeping. Because they could be mass-produced and to a reliable accuracy, this meant that in the 1600s, people all over the UK, Europe, and even the newly discovered world could tell the time without referring to the solar clock. Once set, a pendulum clock can run for weeks and still be accurate within a minute or so. But pendulum clocks do have one major failing, and that is they hate being moved, whether it be on a mantelpiece or in heavy cabinets on the ground like these grandfather clocks on our screen here. But they are rarely moved. John Harrison was acutely aware of this problem, and the reason why he developed his kind of clocks was not to measure time more accurately than the simple pendulum, but to make a movable clock to be carried aboard ships so that sailors and navigators could carry accurate time with them. Now, he achieved this by abandoning the use of gravity to make the pendulum swing to and fro, and went back to the very old idea of using a spring. The key was not to use a simple pendulum, but one with weights at both ends. And to achieve absolute stability when the clock was moved, he used two of these pendulums, linked to each other, and swinging in opposite directions like we have here. So let's show you the problem we have now with moving pendulum clocks, with the aid of these two simple pendulums. The one on your right is going to act as our reference pendulum and is going to stay still. And the one on your left, we've got on this trolley here with wheels so I can move it around. So, with a bit of luck, if I start them both going, you can see that they're beaten at the same time with each other. However, once I start moving the trolley around, you can see that it suddenly starts flowing out of sync. And in fact, the more I move the trolley around, the more out of sync it becomes. However, once I stop the trolley, it starts ticking at a regular rhythm again. It's the act of moving that throws them out of sync. For comparison, if I start the Harrison clock moving, and then move this trolley around, you can see that any movement doesn't affect the rhythm of the pendulums. Because they are linked by the spring, any acceleration in one of the pendulums is offset by a slowing down of the other to an equal amount. Now, several of John Harrison's original clocks still exist today and are housed at the Royal Greenwich Observatory in South London. They still run as beautifully now as they did 300 years ago.
Good evening. My name is Wayne Jarrett. Now, time is not a human invention, but the units we use to measure time are. All animals have their own heartbeat, and as such have their own internal clocks. In fact, all living systems, including ourselves, act as clocks because we depend upon the sun for warmth and for light. But as humans, we do have trouble distinguishing between events which happen on timescales of less than a tenth of a second. Individual sounds tend to merge together and form a continuous tone or a musical note if they last for and are repeated in less than a tenth of a second. Have a listen to this. Oh, and if you were to measure the time it takes a human to react to an unexpected event, well, if you could measure that time, you'd find that it's just about 1/10 of a second. Now, if you checked your own heartbeats once you'd calmed down, you'd find it settled to be between about 60 and 80 beats per minute. Now, that means our hearts tend to beat out a natural rhythm of 1 every second. Down here at the front of the stage, you can see a chart. Now, in fact, this is a timeline, and we're going to use this to plot some of the facts we discovered during this lecture. So right here at the center, we have a 1-second marker. And as I said, this is the same as 1 heartbeat. Now, to the right of this, we've marked some numbers. So we have 1,000 seconds, 1,000,000 seconds, and at the end, 1,000 million seconds. In between that, we have some smaller white marks, and these are simply 10 times the previous. So if this is 1 second, we have 10 seconds here, 100 seconds, then we're up to 1,000. And this continues till the end. So you can also see where we've marked an hour, where we've marked a day, and also a year. And your lifetime, which we're taking to be an average of 70 years, is just here at the end. Right about here. Now we can also use our timeline to plot the accuracies of the other clocks we've looked at so far. And we can do this by answering another simple question. If a clock were started at the moment of your birth, how far out would it be at the end of your lifetime, after around 70 years? Well, we can see our human clocks performed about here. But if we look at Harrison's clock, we find that over the course of a human lifetime, it would accumulate an error of just an hour. And that's just here on our timeline. Now, although Harrison wasn't primarily concerned with inventing everyday clocks, many of his solutions for improving his own clocks were incorporated into mass-produced clocks, and even pendulum clocks were significantly improved by him. Now, these pendulum clocks are still far easier to produce and are much more accurate over longer periods of time than spring pendulum clocks like Harrison's, but only if they're kept stationary, as we saw earlier. By the start of the 20th century, they could achieve astonishing accuracy. So plotting these on our timeline, the best pendulum clocks ever built would accumulate an error of just a few seconds in 70 years.
So, the clocks you've considered so far have a natural beat of about 1 second. But in the last 100 years, another major evolution has occurred, and that has been with the arrival of electronics. Now, electronic clocks beat on timescales of 1,000th, a millionth, or even 1,000th of a millionth of a second. So we now need to open up our timeline to the left in order to consider timescales of very much shorter than a second. Here, just to the left of our 1 second marker, you can see a measurement at 1/10 of a second, which, if you remember back to the big explosion earlier, is about the lower limit of human time. And just as Wayne described about the right-hand side of the timeline increasing, here to the left, each measurement down the scale is 10 times less that of the previous. So from 1/10 of a second, we have 100th, 1,000th of a second, 10,000th, so on and so forth, till we get to 1,000th of a millionth of a second. Now, roughly speaking, there are as many of these timescales in 1 second as there are seconds in your whole lifetime. So let us continue now by looking at 2 clocks that have been developed in the past 100 years or so that combine both mechanical and electrical engineering techniques. The first of these is the quartz clock or wristwatch. Now, a quartz clock simply has a solid block of crystal, and this crystal is made to vibrate by applying a voltage. So you could think of it as rather like a block of jelly, but much stiffer. Now, the quartz crystal on our wrist vibrates extremely rapidly, not once a second, but about 30 30,000 times per second. And in the long term, they give us an accuracy about the same as the Harrison clock that we marked earlier. So again, let's mark this on our timeline as well, so we've got something to compare to later. So the quartz clock, like I say, is an accuracy about here. Now, probably one of the greatest revolutions in timekeeping took place in around 1950, and that was with the invention of the atomic clock. And this is the second of the clocks we'd like to look at now.
An atomic clock is controlled by atoms in a gas. Cesium atoms can be made to flip between two possible energies by illuminating them with microwaves. The frequency of the microwaves is tuned until the maximum number of atoms flip from one energy to the other. This frequency turns out to be exactly 9,192,631,770 times per second. This controls the vibrations of a quartz crystal, which in turn controls the clock.
So today, 1 second is defined as the time it takes a cesium clock to tick 9,192 million, etc., 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 times per second. But just to give you a feel for the accuracy of these clocks, currently 2 atomic clocks started at the moment of your birth would disagree by a factor of as little as 1/10,000th of a second in 70 years. So let's mark that on our timeline. 1/10,000th of a second is about here. And incidentally, CS is the chemical symbol for cesium. But beyond even this, 2 of the new super-atomic clocks, which are currently being developed at the National Physical Laboratory in South London, would reduce this disagreement by a factor of another 100 to be as little as 1/1,000,000th of a second in 70 years, which is about here on our timeline.
Now, the original reason that John Harrison invented his clock was to allow navigators to work out where they were anywhere in the world. Now, they would do this by comparing the time in Greenwich, which they carried with them on his clock, with the local sun time, wherever they found themselves. Now, this was the best they could do back then, but today, we can use our new super-accurate atomic clock to work out exactly where we are with much more accuracy and greater ease. In the 1970s, the American government launched a system of 24 satellites into orbit above the Earth. Each satellite carried its own atomic clock, but they were all synchronized, so they read exactly the same time. Every second, they send signals down to the planet saying exactly where they were and what the time was when they sent the signal. This system is known as the GPS, or the Global Positioning System. And now all somebody on the ground needs is a radio receiver capable of receiving 4 or more signals from any of the 24 satellites to work out exactly where they are anywhere on the globe. Now, we're going to imagine that I'm an explorer, but I've managed to get myself lost. I'm not very good. But luckily for me, I have my trusty GPS receiver with me, which is Kelly, and with her help, we're going to find out exactly where I am. So we're going to look at the series of steps that a real GPS receiver goes through to work out the position of its owner. So if you come a bit more to the center with me, you can see we have 4 satellites on set, 2 over here and 2 on this side. Now I've explained how these work. They send signals down to the planet every second, we note the time of arrival, and use that in our formula to work out the distance from the satellites. So if we receive a signal from this satellite here, we can represent the distance with an accurately measured piece of rope. Thanks, Paul. So Kelly, if you take this from me, put your finger through the loop and find a point on the stage where this is quite taut, so you'll need to go back a bit. Okay, just about here. Now clearly this isn't enough information. We need more signals. So let's receive one from this satellite. Right, so we do the same thing again. So if you take that in your finger, a bit closer, you find a point where both of these are quite taut. So if you come backwards a bit, that looks good.
With signals from 2 satellites, we can get an approximate fix on our position. If we add a 3rd signal, it looks as if we know exactly where we are. But there's still a problem. The quartz clock in our GPS receiver is slightly inaccurate, and so the calculated distance from each satellite is wrong by the same amount. We need a 4th signal to reset the clock in our receiver. This will enable us to correct our estimate of the distance from each satellite so that all 4 signals meet at exactly the same point. Kelly now has all 4 ropes in her hand, and she's about to use the 4th rope to make the necessary clock adjustment.
So if I take these from you and ask you to put your hand around them and gradually slide your hand upwards, yep, that's it, keep going, about there. Now if you bring it down for me and see if you can find a point where they're all quite taut, which is just about here. So because they all meet here, this would be our position. But further than that, we now have a GPS receiver with a clock which is tuned to atomic clock accuracy. Right, thanks very much, Kelly. I'll take the ropes back. A round of applause for Kelly, please.
Let's have a look at an example of GPS in practice.
Hello, I'm out and about in London, and I'd like to show you how I can find exactly where I am using my GPS receiver here. All I need to do is turn it on. What we first see is a circular signal, which shows us what satellites are overhead at the present time. And then below it, we've got some empty boxes, which is showing we're receiving signals from about 8 or so of these satellites. It then processes these signals and starts to work out to find exactly where I am. It then switches to a second display. Now, this display might not look too helpful, so I'll explain what it is showing us. It is plotting our position on the British National Grid. Now, this is what BNG stands for, and it's actually the 1 kilometre square grid that is found on all Ordnance Survey maps you can buy from the local shops. It also tells us that we're on sheet TQ, and the numbers after this plot our position from the left-hand bottom corner of this sheet. So the first number plots our position east, and then the second number plots our position north. It also tells us below that the current time to atomic clock accuracy. So now I've got my readings on my GPS receiver, we need to plot them on the map now to find out exactly where we are. So if I open up the map at the right place, we can start to plot our readings. The machine is telling me that we're at 38440 80153. So the first number tells us we're at 38440. So this is the grid reference for 38 and the grid reference for 39, which is 39 kilometres east from the bottom left-hand corner of the square. So 38440 is a line going up about here. The second position tells us we're at 80153. So here's the grid line for 80, and here's the grid line for 81. So 80153 is a line about here. So we're at the intersection just here. And I'm sure you can recognise this circular building over here. Okay, I may not need GPS to find my position when I'm standing near a famous landmark, but if I was lost in this sort of terrain, GPS would be invaluable and could even save my life.
In the first programme, we saw how the invention of the atomic clock, with its super-accurate timekeeping, allows us to work out our position anywhere on the Earth by using Global Positioning Satellites, or GPS. Now we're going to see how GPS is helping to revolutionise the way we make and use maps. On the outskirts of Southampton, an Ordnance Survey team is getting to work, entering a new development onto the map.
According to my GPS receiver and this Ordnance Survey map, I should be standing in the middle of some fields. But as you can see, I'm surrounded by houses. So this map must be out of date. Well, I've come to Southampton to meet Adrian and Paul from the Ordnance Survey, and they're going to show me how one of these maps is updated.
Okay, Wayne, pull it tight.
Okay.
Any new feature or permanent building over 6 square metres gets recorded.
Okay, Adrian, the width of the building is 8.5 metres.
The theodolite measures the distance between itself and the handheld prism. It knows where it is to within a few centimetres because of a GPS reading. At the end of each day, all the data is transferred to the main computer.
Okay, I've got that point.
The measurement's ready to take, okay?
Right.
I must admit, I was surprised at how much work went into it.
How many of these do you have to do?
We do it for every change in direction of the curb line.
I've got that point.
Okay, he's got that one. We'll move on to the next one. Okay, upright. Okay, I'll let Adrian know it's ready. Okay, Adrian, measurement's ready to take.
That's a lot of detail though, isn't it?
Yeah, what we do is we have to meet a specification where our customers want certain requirements and we have to supply them with that data.
Okay.
Okay, he's got that one. Ready, move on to the next one. All right. Okay, right in the corner. Upright. Okay, Adrian, if you could take the point, please.
So how long will it take you to do an estate like this one here?
Well, it tends to find the estates are actually ongoing. So we wait till there's a significant amount of change, we come back and then survey that change and maybe visit again 6 months later.
Okay, thank you for your help.
Here on my computer, I have an electronic map of the Millennium Dome here in London. And we've got it connected to a screen here, so hopefully you can see what I'm doing. On the left-hand side, we have a menu with about 40 items on it, each of which corresponds to its separate set of features on the map. You might like to know that the system actually knows 400 of these different feature databases, but we've only got 10% here just to give you a flavour of it. So as a user, I can select those areas that interest me. So for example, the building outline. I'll turn that on and hopefully you see the building outline and all the other buildings appear around the dome. Again, I can turn on the public roads. And you might well have noticed the 2 red lines appear from the top left of the screen. Now, I suppose that some of you are asking, why have we just had a road suddenly appear slap bang through the Millennium Dome? The reason is because this is an underground road called the Blackwall Tunnel. And it actually runs both underneath the river and the dome itself. But I can use the electronic map to do something else as well. I can zoom into areas of more detail or areas that interest me. So for example, I can zoom into these buildings here, which just look like buildings, until I turn the house numbers and names database on. And then the system identifies them to me as numbers 1 and 2 Blakely Cottages. Incidentally, I can also zoom into this area here in the dome itself. And you can see that it's the ventilation building. But it's not actually the ventilation building of the Millennium Dome. It's the ventilation building to the Blackwall Tunnel that I was talking about earlier. But because it's a listed building and they couldn't knock it down, they actually had to build the whole dome around it. This gives us a clue into a whole new way in which electronic maps can be used. So let's explore one example in a little detail. Suppose I have an electronic map like we've just been looking at, a GPS receiver and a portable PC all installed together in a car. We now have the key ingredients to set up an in-car navigation system. Right, so I suppose I want to go to the supermarket, which I know is on the junction of Selsdon Way and East Ferry Road. So I've just tapped into the in-car navigation system, both these roads, and now it's brought me up a map of which route I need to take. Now, there are 2 possible ways from this roundabout, so we'll see which one the system chooses.
Roundabout 300 meters ahead. Take the 3rd exit. Exit road at 2 o'clock.
3rd exit, 2 o'clock. I guess we go straight on.
300 meters to a right turn. Then a right turn again.
Now, if I want, I can watch my progress on the moving map, but I don't really want to take my eyes off the road. I think I'd just rather listen to the instructions.
Perform a U-turn.
Unfortunately, Heidi had missed the second right-hand turn.
The makers claim that the system will recalculate a route if I get off track, so let's see if it will do it.
Turn right.
Okay, it's just given me a new route. Let's try again. Ah, this looks a bit better. Here's my right turn.
Keep following this road. 100 meters to a left turn, then a left
Oh, so it's taking me to exactly where I want to go. Here we've got Asda.
So we've seen electronic maps combined with the ease of recording geographical information using our GPS system has changed the way that maps are made. So instead of you having to know where you are on one of these, it's possible for a map system to know exactly where you are and change the data it shows accordingly. We have here a computer with a CD-ROM database which contains map information. Now, in addition to information which you'd find in a normal map, it contains details on postcodes with information on houses, schools and other buildings within each postcode location. So we need a volunteer to help us explore this map. Hi there, and your name is? Joel. Where are you from, Joel?
I'm from King Solomon.
From King Solomon. Okay, if you come around here for me, and stand there behind the computer. Okay, so let's imagine that this is Joel's first time in London, and he wants to see all the big places, the palaces, the parks, and all the other attractions, but he really wants to see the Tower of London, but he doesn't know where to go. Well, our map system can help. You can see that there's a dialog box into which we can put places, names of places or postcodes that we're searching for, and then our map system will find them for us. So, if you go down to this box here, and you type tower, that's it, then a comma, a space, and the word the. There we go. Oh, got this 8 there. That's great. Okay, hit return for me. In a few seconds, our system generates a map centered on that location. Now, if you click on the eye for me, that will magnify the map. Great. So now the map's magnified, and you can see the Tower of London is in the center of the picture. So now we would know exactly where we want to go. But going around the tower is quite tiring work. And let's assume that Joel's hungry, and he'd like to get some food, but still he doesn't know where to go. We can still use our system. If you click on the pair of glasses just there at the top, and then click on the down arrow once for me, our system presents us with a number of places that we can search for. So we could look for bookshops, we could look for dentists or newsagents. But because we're looking for food, we're going to search for takeaways. That's the one, and then click on start. So now our system updates itself again, and we can see some new icons, and they show us where the nearest takeaways are within a 1 kilometre radius of the Tower of London. But we still don't know what they are. So let's find out. If you click just there on the open book, and then let's select the one nearest the tower, so that one just there. Right. Well, I can see that Joel's actually selected a McDonald's restaurant, and it's found at 12 Tower Hill Terrace, and we also have the postcode. So now we would know exactly where we need to go. Well, thanks for your help, Joel. A round of applause for Joel, please. Now, I've zoomed into another level of detail on our map system, and I'm centered the map on the White Tower within the Tower of London, and I'm told this is where the crown jewels are kept. Now here, you can see some stairs which are leading up to the tower. On this side, on the right, you can actually see the thickness of the walls of the tower. And it's possible to find out where the doors and where the windows are located. So this shows you what amazing detail we can summon almost instantly from one of these map systems. Now, of course, this is nothing new. Maps like these have been available on paper to special order for a long time. But these maps are now stored electronically, and so they could become available over the internet, and we'll all be able to access them far more easily. But the real revolution still hasn't begun, because the word map isn't interpreted as widely as it could be today.
A British firm called the Geoinformation Group has been taking aerial photographs of the whole of the UK and aligning them to the Ordnance Survey maps. The camera is mounted in the floor of the aircraft. The photographs are taken on large colour film, 9 inches square. The aerial photography unit is part of Cambridge University and flies out of Cambridge Airport. The flight plan takes the pilot in a series of parallel swoops across the landscape so that a series of slightly overlapping photographs can be taken. The camera is controlled by a laptop computer, which takes 180 photographs an hour at a height of 5,000 feet. The photographs can be used for a range of different jobs, helping to solve land disputes, emergency planning for floods, the sighting of masts for mobile telephones. They're even used by the builders of penthouse flats, looking for a suitable roof. Once the colour negatives have been scanned into the computer, they can be matched to the grid lines on the Ordnance Survey map. Here you can clearly see an intersection on the edge of the village. Because of the high resolution of the image, the photo can be magnified to show even more detail. The photos can be edge-matched and their colours combined to make up a single photograph of a very wide area. This is Ayr in Scotland. At the very highest magnification, you can see many of the details in people's back gardens, right down to objects only 25 centimetres long.
This is clearly another astonishing piece of technology. But in addition to all this, electronic maps can also show information to us in ways which are far more easily visualized than it would be for us to imagine the same thing on a paper map. For example, our map system can read the contour lines from a map, and it can use those to generate a 3D surface of the landscape onto which it can lay the same map. So it appears to us that we're looking down on the landscape with all its hills and its valleys as though we were flying in an aeroplane. But our system also knows where there are roads and trees and rivers and other details, so it can use these to build an even better picture of the same space.
Now, the makers of a computer game called Rally Championship wanted to make the game look as realistic as possible. So what they did was travelled around the country taking photographs of over 400 miles of proper rally stages. They then superimposed these onto the Ordnance Survey map data to get the hills and the valleys, and then used both sets of information to create their animated graphics. Now, as you can see, we're here by a rally car now, and I'm going to take a ride with Ernie as his co-driver on one of these proper rally stages. And when we've finished, we can then compare it against the game.
Okay, Heidi, put your seatbelt on,
Right.
and then we can go.
3, 2, 1, go! 70, right 2.
The photographs they took of the rally stages helped to make the colour and shading on the road, the grass and the trees look very realistic in the game. Getting up to 80 miles an hour now. While I'm herring around here, Wayne's got a volunteer to drive over a very similar stage of the Rally Championship game.
That's right, keep it going, you're doing fine. That's fine. This is what we love to see, cross-country driving, it's the best.
2, left 2.
Right, one easy left there, that's
150,
right.
right 5.
You can follow the car's progress on the Ordnance Survey map in the bottom corner of the screen. This map is so accurate that you could use it to navigate your way through the stage.
Oh, mind the tree, mind the tree. Mind that tree as well. That's all right, keep going. Right, jump on the brakes, that'll reverse it a bit. That's the one, turn around for me. Okay, off we go again. We're doing good, we're doing good. You've got a foot on the floor this time.
30, left 4.
Well, before Kemi gets too used to this, I think we better stop this. I know she's enjoying herself far too much, but you've done very well. I think that deserves a big round of applause. Thanks for that, Kemi.
Well, thanks, Eddie. That was absolutely fantastic. But I think next time I'm going to play the game from the comfort of my own home.
But let's think about this a bit more seriously. Computer simulations are already of massive importance to both aircraft pilots and the military, where accidents in training can endanger lives. Now, creating realistic virtual worlds like this is very expensive. But if things go the way we've indicated, then the training possibilities will be immense. And you too could learn to drive in your own bedrooms, instead of being out there on the M1.
But when you are on the M1, wouldn't it be extremely useful to have one of those in-car navigation systems that we were talking about earlier? And we can make it even better by adding a communication link, such as a mobile phone. With this link, it's then possible to receive up to the minute, now forget up to the minute, we're talking up to the second, information on the road network, such as there being traffic jams or roadblocks, or woe betide, even crashes. So if a potential roadblock does lie ahead, the system can then identify an easier new route for you.
On the screen, you can see some pictures of devices which are available today on the high street, and we feel they indicate clearly where things are moving. Now, these are examples of PDAs, or personal digital assistants, and they're basically small laptop computers. Now, some of them already incorporate mobile phones. Some mobile phones have their own GPS navigators, so these phones know exactly where they are. Soon, we'll be able to combine all of these separate units into a single portable unit that can talk to the databases that we've been describing. Now, perhaps the biggest problem that still remains is how to combine a large screen that we all like for easy reading with a small, transportable pocket device. Well, some people say the solution lies in screens that can be folded or rolled away, much in the same way that we fold a paper map. Or maybe something that could be put into a pair of glasses. Only time will tell. Our Faraday lecture began with John Harrison's solution to one of the greatest engineering challenges of his day. And we've gone on to show that engineering has opened up to us a whole new world of possibilities. Michael Faraday started a process over 100 years ago, and this has led to the widespread use of electricity and electronics. Now, the world of electronics is already huge, but the future of electronics is limitless. It offers every one of you in the audience great opportunities as well as great responsibilities for the future. And as a result of what you have seen today,
we hope you will go away excited,
entertained,
and inspired.
Thank you.
you.